This conference will now be recorded.
Hello everyone. Chemical properties of aldehyde and ketones we have started already, and the first type, which is nucleophilic addition, that is already finished. And then the next type is oxidation reaction. Under oxidation, the first two types of reactions are done, and we are starting now from number 3, which is haloform reaction. And under this oxidation reaction topic, there will also be another term, which is taste for aldehydes, because when we are talking about oxidation and the taste of aldehydes, that is the distinguishing taste of aldehydes, by performing this test we can differentiate whether it is ketone or aldehyde. Now that is also based on oxidation, so that is why it will also be discussed under the topic oxidation reaction, and there will be also related problems. After finishing that, if time permits, we will also discuss the next type, which is reduction reaction. So let's start with oxidation reaction. Number 3 types of oxidation reaction is haloform reaction. From the name you can understand haloform. That means we will obviously use some halogen. So in this reaction, it will be positive only when there is CH3CO group present. That means ketomethyl group must be present. This fragment must be present. And when methyl ketone, that is, I'm talking about this group, methyl group and ketone, so that is it is methyl ketone fragment. When methyl ketone is treated with the halogen, any halogen, chlorine, bromine, iodine, in aqueous sodium hydroxide, that means basic medium, then what happens? First, polyhalogenation occurs. So what happens? All these three hydrogens are basically alpha hydrogen with respect to carbonyl group. All these three hydrogens are replaced by halogen. If you look at this example, here we have taken the simplest ketone, which is acetone, CH3COCH3. So here one of the methyl group, all the hydrogens are replaced by chlorine atom, because in this case we have taken chlorine as halogen, and anyway which is the medium. So first there is polyhalogenation of all these three alpha hydrogen, followed by cleavage of the methyl group. So next step, what happens? Now this CC bond is broken. So from the left hand side part, CCl3, what we get CHCl3, and the other side is CH3 CO2 Na. Now as the medium is basic, obviously it will not remain in carboxylic acid form, it will remain in sodium salt form. Further, if you acidify it, you will get carboxylic acid. So here the resulting products are carboxylate ion and it is trichloro. You can also write in general that it is trihalomethane. Trihalomethane, because methane is CH4. Now trihalomethane means 3 hydrogens of CH4 molecule. If you replace with halogen, then we will call it trihalomethane, because it is after all methane derivative. So this is the product combination, right? Now there is only one aldehyde that can undergo this reaction. Now which aldehyde it is? We know the simplest aldehyde is HCHO, that is formaldehyde, and the next member is CH3CHO. Now only in this aldehyde you can find the group methyl ketone, that is CH3CO part is present. So that is why only this aldehyde, if you consider all the aldehyde molecules, this is the only aldehyde that will give positive haloform reaction, right? Because the previous member HCHO, that there is no CH3CO group. If you consider the next member, which is propanaldehyde, that is CH3CH2CHO, but in that molecule you do not have any methyl ketone group, so that is why it will not be positive. So this is the only aldehyde that will give haloform. Now under haloform, if you consider only iodine and NaOH, that means chlorine, bromine, iodine, we are considering only iodine. So in that case, the corresponding CHX3, this is actually the general form. So when I am using iodine, then it will be CHI3. Now as you can see, CHI3, now iodine, 3 iodine atoms compared to chlorine and bromine. Now obviously the molecular weight will be high for this one. So only this molecule, as it is solid in nature and there is specific color which is yellow, and there is precipitation, because in the medium it is not soluble, there will be precipitation. And we know whenever there is any precipitation or any particular color formation for the product, you can use that test as identification test. So for identification of the group CH3CO, whether it is present or not, if you want to check, you can perform haloform, but not just any haloform. You have to use iodine NaOH, which is, you can also call it as if it is iodoform. Okay, so depending on which halo you have taken, different names may be there. It may be chloroform, which is CHCl3 in this example that you are seeing. If it is Br, it is CHBr3, name will be bromoform. If it is iodine, it is CHI3, name is iodoform. And only this last reaction you can use for identification purpose, that is to check whether CH3CO group present or not, because in this case only there is precipitation. If there is no precipitation, how we will understand whether reaction is occurring or not? Okay, so that is only the last type you can use for identification purpose of CH3CO group. So we will focus on this iodoform reaction now. When the halogen used is iodine, then the haloform reaction name will be now iodoform test. It can be used to identify whether methyl ketones are present or not. That is, in any ketone, whatever you take, if one side of the carbonyl group there is methyl group present, then only this test will be positive. Because why only iodine chosen? Because here the compound is yellow solid with characteristic odor also. Now, not just CH3CO, if you have any alcohol with the general structural formula as given below. So see this type of structure. So this type of fragment CH3CHOH must, if it is present, then also the reaction will be positive, because in the medium the CH3CHOH part that will be oxidized to CH3CO, and we know whenever there is CH3CO group, haloform reaction is positive. And here we have R, this R may be H, it may be alkyl, or it may be aryl. And after haloform, from this that is CH3, it will be removed in the form of CHI3, which is actually iodoform. This molecule is known as iodoform, and there is precipitation. Other part it will remain in anionic form. If it is NaOH, it will be sodium salt of RCO2H acid. So alcohols that have general formula as given below, that is CH3CHOH, that can also give positive iodoform test, because under the reaction condition, this fragment will be oxidized to the corresponding methyl ketone. So for example, suppose if you have taken ethanol. Now ethanol is CH3CH2OH. So if I am writing this in this way, CH3CH2, I am writing these two hydrogens separately so that you can understand it clearly. Now here this fragment is present, and it can be converted to ketomethyl. So now it is basically converted to acetaldehyde. So in case of ethanol, it will be oxidized to acetaldehyde. Then further reaction, it will be positive. Okay. So this is the only alcohol which can give positive iodoform test. So this reaction is, though we are discussing under chemical properties of aldehyde and ketones, but remember it also has some other application related importance, which is this reaction can be used, though not just any halogen, you have to use iodine. Then only you can call it iodoform, and this reaction can be used to check whether CH3CO group or CH3CHOH type of fragments are present or not. Because in that case only there will be a positive test which you will be able to understand by this yellow solid precipitation with characteristic odor. Based on haloform reaction, here we have a problem. After completion of these two reactions, here two reactions are mentioned, reaction 1, reaction 2. So reaction 1, we have taken 1 mole acetone and bromine 1 mole NaOH, basic medium. Second reaction, again we have taken 1 mole acetone, again bromine 1 mole, but the difference is now the medium is not basic, medium is now acidic. Which acid we have taken? Acetic acid. So after completion of the reaction 1 and 2, the organic compound or compounds, both may be the case, in the reaction mixture is or are. Here we have given PQRSTU. Total 6 molecules are given. And look at the options. It is saying that for reaction option A, reaction 1, you will get only P molecule. That is the first one, CH3CO, CH2Br. Reaction 2 also you will get this same molecule. Then reaction 1, you will get U, that is the last compound, CHBr3, because it is bromoform reaction. So obviously CHBr3, which is, if you remember, the general structure is like this. So when you use bromine, obviously it will be bromoform. And for reaction 2, there is formation of Q and acetone. Acetone is basically starting material. Option C, there is formation of T, U as well as acetone. That means T will be formed, U will be formed, and some unreacted starting material, which is acetone. And reaction 2, you are getting only P. D option, reaction 1, you are getting R, unreacted acetone. And from the second reaction, you are getting molecule S and unreacted acetone. Now, in the previous slide, we have seen haloform reaction where we have done it in NaOH medium, basic medium. But we do not know what happens if it is acidic. Don't forget about the acidic condition. Just focus on what happens if it is basic medium. We know when it is basic medium, there is formation of CHBr3 and sodium salt of the corresponding, that is CH3. As here we have taken acetone, so this CC bond will be broken. This side, this carbon, it will be we will get this carbon in the form of CHBr3, and the other part CH3CO, that we will get in the form of sodium salt of carboxylic acid. Now if that is true, that means we should get T and we should also get U. Now T and U in reaction 1, that is present only in option C, right? Because in other options from the first reaction, T and U not mentioned. In the first option it is mentioned P, but we do not get this type of product, that we have already seen. So see, just this much information is enough to choose the correct option, which is C, right? Because T and U both present for reaction 1, that you are getting only in option C. But why there is also mention of acetone? If that question is arising in your mind, then the answer is you have to know what is the mole ratio that we have taken, because we have not talked about mole ratio in the previous slide. Now if you write the actual balance equation, it is something like this. CH3COCH3, it is 1 mole. Now 1 mole of the ketomethyl group containing carbonyl, you should need 3 moles of bromine. Otherwise reaction will not be there. And 4 NaOH. Though NaOH in this case we do not require, but still you should know this is a balanced equation. If you consider both side number of same carbon, all the atoms, if you want to be same, both side, product side, reactant sides, and this is the reaction, a balanced reaction. Now it is 1:3, but what we have taken? We have taken 1:1. So here the limiting reagent is CH3COCH3 and bromine should be present excess 3 times more. But bromine you have taken 1 mole as it is mentioned in the condition. So for 3 moles of bromine, requirement is 1 mole of ketone. But if bromine is present 1 mole, then only 1/3 of starting substrate, that is carbonyl, that will react. So if it is 1/3 of acetone is reacting, because in our case acetone is the carbonyl compound, and if it is only 1/3 of acetone reacting, so this product, which is basically 1:1, if acetone is 1 mole, then this will also be formed 1 mole. So though 1 mole is there, but only 1/3 will react because enough bromine is not present, only 1 mole bromine present. Now if 1/3 mole of acetone is reacting, obviously 1/3 mole of sodium acetate you will get. So some acetone will remain in the medium, so that is why acetone is also present as unreacted starting material. Now this is for the first reaction. Now what about the second reaction? Because second reaction is not basic medium. Now remember, iodoform formation, it is possible only in basic medium. If you are using acidic medium, Now the mechanism is completely different, and here some different types of reaction actually occurs. So see, this is the actual reaction that occurs if you have taken acidic medium. Now in this case, this is 1:1 relationship between bromine and CH3COCH3, and here what happens, only one alpha hydrogen is replaced by one halogen. So CH3CO CH2Br, this will be the product, and the H that is replaced by Br, that H and another bromine together, it will make the side product Ag. So CH3CO CH2Br, this is basically molecule P, and that you will get in which reaction 2. That means option C is matching for both acidic reaction, which is reaction number 2. This is reaction number 1. Now if you are curious to know what actually happens in acidic medium, you have to consider this type of mechanism. Here we have taken acetone molecule, and this molecule is basically CH3COOH, that is acetic acid. Now under acidic condition, first there is enolization. What happens in enolization? This alpha hydrogen, this carbon hydrogen bond will be cleaved. There will be CC bond formation. This CO double bond will be broken. There will be negative charge over oxygen. Ultimately, it will be enol. Now, the enol in presence of bromine molecule, what happens? Now, see the lone pair over oxygen, that is making a double bond here, and CC double bond is broken. It is attacking Br. Br bond is also broken, and finally this H will be removed. So what you are getting? It is simply one alpha hydrogen of this methyl group that is replaced by bromine, and this is molecule P. So considering all this, correct option will be option C. But remember, if you are getting this type of question and if you do not know what happens in acidic medium, keeping all the other things same, just like haloform reaction, then also you can answer this question if the options are like this. Because we know when it is basic medium, there is formation of the sodium salt of the corresponding acid and CHX3. In this case, CHBr3, because we have taken bromine. So obviously T and U will be formed. So T and U both present only in option C. So this much information is enough to choose correct option C. And acetone is also present because we have taken 1:1, but it should be actually 1:3 if you want complete reaction, because acetone is the limiting reagent. Bromine should be extra, but we have taken 1:1. So that is why some excess acetone will still be present. And in option C, it is also written that for reaction 1, there will be T, there will be U, which are actually product, but also there will be some amount of unreacted acetone. Fine. So as I have said that under oxidation, finishing the haloform, actually all the reactions we have discussed, but now the reactions that we are going to discuss, they are also oxidation, but these oxidation reactions are basically the distinguishing test for aldehyde. So that is why the topic is test for aldehyde. So if you have any compound and you want to know whether it is aldehyde or ketone, you have to do this test. This is distinguishing test between aldehyde and ketone. The first test for aldehyde is tolerance test. This is also known as silver mirror test. This test is qualitative laboratory test which is used to distinguish aldehyde and ketone. Now, what fact is exploited in this reaction? We know that aldehydes are very good reducing agent. They are easily oxidized, but ketones are not easily oxidized. Remember in the last class we have seen that if you want to do oxidation for ketone, you have to use very strong oxidizing agent or very drastic condition, because only if you do so, then CC bond cleavage is possible. But if it is aldehyde, there is no CC bond cleavage, it is CH bond cleavage, which is much more easier. So that is why for aldehyde oxidation reaction is easier, but for ketones that is not the case. So we will exploit this fact because there is difference in reactivity. So what we do in this reaction? We take aldehyde, then there is presence of basic medium and Ag plus. But Ag plus is not taken in this way, it is taken in some salt form. But what happens? Aldehyde is oxidized to carboxylic acid, though it remains in the anionic form because the medium is basic. Acid cannot remain in acidic form in basic medium. It will remain as RCOO minus. But further, if you do acidification, final product will be carboxylic acid. So here aldehyde is oxidized to carboxylic acid. Ag plus is reduced to Ag0 from +1 state. Now it is metallic state, that is elemental state. And this is actually responsible for the silver mirror that is formed in the wall of test tube in which we are doing the reaction, and water. So what is Tollens reagent? It is a mixture of liquid ammonia and AgNO3. So AgNO3 with ammonia, it forms some silver amine complex. But the important point that you have to focus here, Ag plus is the actual oxidizing agent because it will accept electron from aldehyde. So this is Tollens reagent which can oxidize aldehyde, not just aldehyde, if there is any alpha hydroxy ketone type of functional group. Alpha hydroxy ketone means C double bond O. So the next carbon, this is actually alpha carbon. So if this alpha carbon is containing OH, this is, you can call it alpha hydroxy ketone. So if this type of compounds are present, that will be oxidized to corresponding acid, and the precipitation of elemental Ag, which is actually give you this characteristic silver mirror on the inner surface of the reaction vessel. So if it is test tube, it will be something like this. So see, this is before the reaction, or you can say if the test is negative, if aldehyde or alpha hydroxy ketone not present, this is clear solution, no mirror. And second reaction is also positive, but sometimes what happens, the mirror is not formed very well, or maybe it will take some more time. But if the reaction is, if you have done it well, then you can see the mirror is formed, and this is actually the silver, elemental silver. Now, as it is mentioned here, the terminal alpha hydroxy ketone, it is not just any alpha hydroxy ketone, terminal alpha hydroxy ketones, if it is present, then that also can give this type of taste. So terminal alpha hydroxy ketone is COCH2OH. I am drawing it here. C double bond O. This side there may be any group. Then COH. But as I have said terminal, that means this carbon further no group. There is only 2 hydrogen. So this type of molecule is present, terminal hydroxy ketone. They can also give positive test because they have the ability to tautomerize to aldehyde. So here tautomerization is possible, and this CH2H group, it will be ultimately converted to CHO group. That is the reason they can also give positive test. And some for extra information, some special cases are also there. Suppose you have benzoin or furoin type of molecule. Now what is benzoin? Benzoin is PHCO, CHOH, And what is furoin? Furoin is same thing, same molecule, only difference is in place of pH group, now we will have furan, heterocycle. So this is called benzoyl or furan. Now see, this is also alpha hydroxy ketone, but they are not terminal. It is non-terminal, but still they can give positive taste. Or if you have any compounds where 2 aromatic rings are very similar type of compounds with 2 aromatic rings present on 2 terminal position, then also reaction may be positive. And if you have 1,2 diketone like dialkyl glyoxal, glyoxal is HCO CHO, that is 2 CHO groups side by side. Now dialkyl means there may be any group, that is H, so it is glyoxal is HCO HCO. Now dialkyl glyoxal means these 2 H, there will be alkyl group. That can also give you positive taste because it is after all 1,2 diketone. Then benzyl. What is benzyl? Benzyl is PHCO COPH. This is also 1,2-diketo. This can also give positive test. And furyl. Furyl is same molecule, only in place of pH you will have furan ring. Furan ring is heterocycle like this. So these are some special cases where the reaction may be positive though there is no CHO group. Okay. Based on this, let's see this problem. An organic compound X, molecular formula given C5H10O. It is phenylhydrazone. That means it can react with phenylhydrazine, because we know phenylhydrazone formation is possible only when there is pH NH2. This reaction we have seen in last class, and some carbonyl group, aldehyde or ketone, whatever. So if it is present, then only phenylhydrazone formation is possible, and it is giving negative response to iodoform test. Now what it means? Negative response means there is no ketomethyl group. Remember, iodoform test we have discussed in the first slide. So there is no ketomethyl group, but there is C double bond O, because it is giving you positive not positive, I mean it is giving phenylhydrazone compound. So based on this information, you have to, okay, one more information is there. It produces N-pentane when you are doing reduction. And the molecule C5H10O. Look at the options for X, 3-pentanone. That means it is ketone, 5 carbon chain, middle carbon 3, containing C double bond. N-amyl alcohol. Now N-amyl alcohol, this is 5 carbon alcohol, the name is such. Pentanal, that is also linear chain, at the terminal position there is CHO, and 2-pentanone, this is basically isomer of the first compound. Only difference, now at 2 position of this 5 carbon chain there will be C double bond. So see, this is the structure for D and this is A, right? Now A, there is no ketomethyl group, and we know this is giving negative test for iodoform, there should not be ketomethyl group, but D, there is ketomethyl group. There is circle, it is showing in this circle. So this cannot be correct option. A may be correct, but we have to know the other compounds. This is N-amyl alcohol. Now alcohol cannot give phenylhydrazone, right? Though after reduction you can get N-pentane, but it will not give you phenylhydrazone. Even this last information is also not present, that doesn't matter. So without this information also you can solve this question. So this molecule cannot give phenylhydrazone. And what about pentanal? Pentanal is 5 carbon, 1, 2, 3, 4, 5, and then CH. Now this molecule cannot give negative response to iodoform. Now this will also give negative response because you do not have CH3CO group, and this can also give phenylhydrazone, right? So it yields phenylhydrazone and gives negative response to iodoform test. So negative iodoform test means there must be presence of ketomethyl group or CH3 CHOH. Now these also not present in this molecule, okay, and it produces N-pentane on reduction. So based on all this information, here correct option will be 3-pentanol. Correct option will be 3-pentanol. Okay, because it forms phenylhydrazone and negative response to iodoform test. And iodoform test, one information he missed. It is negative response to tolerance test. Tolerance test negative means no CHO group. So that is why this compound can also it is not possible. So based on all this information, correct option will be this one. Next problem. This is also based on tolerance. Previous problem is basically based on phenylhydrazone, iodoform, tolerance, and reduction. So many informations are there. Second problem, in tolerance test for aldehydes, the overall number of electron or electrons, it may be one electron or more than one, transferred to a tolerance reagent. Now tolerance reagent, though we have seen it is mixture of liquid ammonia and AgNO3, but actually with ammonia, silver, it forms this type of silver amine complex, coordination complex. There is positive charge which can be balanced by one nitrate ion. But Ag is positive, +1 oxidation state. So it is asking how many electrons will be transferred to the tolerance reagent. That means how many electrons will be transferred from aldehyde to Ag plus to form silver mirror. So this is an integer type of problem. It is because fraction of electron not possible. It is not 1 electron, 2 electron, 3 electron like this. So we have to see the mechanism that as here Ag plus is oxidizing agent, so it will accept electron from aldehyde. Aldehyde is a reducing agent. So what happens here? This is aldehyde molecule, general formula RCHO. So first, if you write this C double bond O as if it is R C dot O dot. So we have broken one bond and we are writing one electron each on carbon and oxygen. Now Ag plus, if it is accepting one electron, it will be converted to Ag. Now this electron, suppose this one. So if it is accepted by Ag, now there will be positive charge over carbon, C. Then the medium is basic. HO minus can attack this carbon plus. Now it will be like this. There is O dot, oxygen carrying single electron. Next, this H, if it is shifted to O dot, now there will be, sorry, not this one. If this H, if this CH bond is broken and this H is moving towards O dot, now there will be carbon radical, and this carbon radical, just leave it like that. In presence of hydroxy ion HO minus, it can accept this hydrogen and there will be negative. So it is radical anion. Now Ag plus can again take this C dot electron and finally there will be formation of RCO minus plus OH. Now this minus and plus, you can easily write it like this, that is RCOOH. That means negative charge over oxygen, positive charge over carbon. Ultimately it is C double bond RCOOH. But it remains in this anionic form because it is basic medium. But whatever it is, important point is how many electrons are actually transferred. So here first electron transferred and we are getting carbocation positive charge over carbon. So this is the first electron and this is the second electron. So it is basically total 2 electrons that will be transferred from aldehyde to Ag plus or 2 tolerance reagent. So when we are saying 2 tolerance reagent, it is nothing but Ag plus because that is the actual oxidizing agent. Again, another problem with based on tolerance test. Which of the following pairs give positive tolerance test? So in each option, you have 2 molecules. So both the molecules simultaneously should give tolerance. If one is giving positive, another one is giving negative, that option cannot be correct. Both the molecules must give positive test. Then only you can choose that as correct option. Okay. First option, glucose and sucrose. Then glucose and fructose. So these are carbohydrate molecules. Hexanyl, aldehyde, acetophenone. Acetophenone is PH, COCH3. And again fructose and sucrose. So first we'll see the structure of glucose and sucrose. So see here we have glucose. This is open structure because it can also remain in the cyclic form. And in the open structure we have aldehyde. So this will give positive test because it can remain in both form. So the non-cyclic form, it can give positive test. And what happens when there is ring formation? This oxygen, the lone pair of oxygen, it attacks this carbonyl carbon. So this carbon oxygen bond formation takes place like this, and there is a 6-member ring. In that case, there is no CHO, but open structure there is CHO. But if you look at sucrose, there is no CHO group, right? So here this is positive, but this is negative. So this option cannot be correct. Now what about the next? Glucose, we know it is positive, but what about fructose? The structure of fructose is CH2OH, then C double bond O, then 3CHOH and CH2OH. Now fructose, this is there is no aldehyde group, right? It is CH2OH, then C double bond O. Now here enolization. See, if you consider this carbon, so this is alpha carbon and these two hydrogen alpha hydrogen. So if this alpha hydrogen, if you consider enolization, CH bond will be broken, there will be CC bond. So this is actually enol formation. Now this enol, what can happen? There are two OH and CC double bond. That means something like this. So whenever you have enol, but both sides there is enol. Now this OH, if it is broken and negative charge over carbon, that means now carbonyl bond, carbonyl group can be formed in this particular carbon, and as a result now you are getting aldehyde. Fine. And when this enol, because this is enol, so from enol again you are getting keto, this is tautomerization. Now when this is occurring, two things possible. CHO group you will be getting in both cases, but this particular carbon, focus on this. In this carbon there is one H, one OH. Now this is the carbon. Now this H and OH, it may be left hand side or right hand side. So that is why two possibilities are there. So basically I am trying to say fructose can yield glucose and mannose, and in glucose and mannose there is free aldehyde group. So fructose, although containing ketone, it should not give positive tolerance test, but still it can give positive test, because under basic condition, we know tolerance test is basic condition. Under basic condition, this type of rearrangement, that is first there is enolization, then again from enol you are getting keto, and during this second conversion two possibilities are there. So because of this type of rearrangement, ultimately glucose and mannose is there. This is C2 epimer of glucose, because if you consider this carbon as two, these two molecules are basically isomer, they are epimer, because only at the one carbon there is difference in the arrangement of H and OH, steady, that is spatial arrangement. So as there is CHO group, so that is why it can give positive. So see, option 2 can give positive test for both this one as well as this one. So this should be the correct option. But why not option 3? Option 3 is hexanal. 6 carbon then CHO. And tolerance test will be positive for this. But what about acetophenone? It is PHCl CH3. There is no aldehyde group. So that is why this is not positive. And last option, fructose is positive, but sucrose, that is negative. So correct option will be second option. Fine. So after finishing tolerance test, the next important test for aldehyde distinguishing test is failing solution test. Again, we will utilize the property that aldehydes can be oxidized easily. When aldehyde is warmed with failing solution, deep blue color of failing solution. Basically, failing solution is containing, we will go into the details right now, just see. Failing solution is containing Cu2+, which is blue, and this deep blue color solution, if you are treating it with some aldehyde, it will be converted to Cu+. So Cu2+ accepting one electron, and it is reduced to copper +1 state, and it will be converted to, that is the color will be converted to red. So there is drastic color change. You can easily understand whether the reaction is positive or not. So this is positive test. But if even after adding to the sample, which may contain CHO, may not contain CHO, because you are doing the test, you do not know. You are trying to see whether it is positive or not. See, if you are not getting red PPT or Cu2+ this type of color, then it means reaction is not positive. Fine. Now remember, if it is aromatic aldehyde, reaction is not possible. So not just any aldehyde will give you failing. It must be non-aromatic, though that problem is not in the case of toluenes. Now, why aromatic aldehydes cannot give? Because aromatic aldehyde is ARCHO. AR may be phenyl ring or any substituted phenyl ring, or it may be naphthalene. Now, why it is not possible? Because with respect to CO, there is no alpha hydrogen. So that is why this reaction is not possible. Next, we will see what is Fehling solution actually. What are the compounds present in it? Fehling solution is prepared by mixing equal volume of Fehling solution A, which is nothing but copper sulfate solution. We know it is blue color, but there is another Fehling solution which is B. So you are adding A and B together. It is a mixture. So what is B? B is basically containing clear alkaline solution of sodium potassium tartarate. Tartaric acid, it is carboxylic acid, and if you take the corresponding sodium potassium salt, because there are two CO2H group, one CO2H group sodium salt, another CO2H group potassium salt. So it is the sodium potassium salt of tartaric acid, we are calling it tartarate, and this is alkaline solution because it is any salt or sodium salt forms, also known as Rochelle salt. Now when you add A and B together, the two solutions later mixed in equal volume to get the final Fehling solution. Now initially it is blue, but this blue and the final blue color, there is some difference. It is deep blue. So the deep blue color, it is basically generated from this type of B tartarate complex of CO2 plus. CO2 plus is coming from Fehling solution A and tartarate salt is coming from B. So together is making this type of complex which is having deep blue color. Now this tartarate tetraanon, that will be the chelating agent for copper 2 plus ion. Though detailed structure, even if you don't know, it is fine. But just try to remember what is A, what is B. One is CuSO4, another one is sodium potassium salt of tartaric acid. And when you mix these two, you get the actual Fehling reagent. A is copper sulfate, B is alkaline solution of sodium potassium tartrate. So tartaric acid is CHOH, CO2H, CO2H. But here it is sodium salt, potassium salt. So you are mixing these two. Copper sulfate in presence of NaOH, it can remain CuOH whole 2, but ultimately it is actually Cu2 plus, right? Now this Cu2 plus, it can also remain in this form, but if you consider this CuOH whole 2 and one H and this OH, if it is removed, there is OC bond formation. Now this is one side of the molecule, but another this type of chelate can also be formed this side, so then it will be B tartarate. So this is actually responsible for the deep blue color solution. So this deep blue color solution, in simple way you can consider it as if it is source of Cu2 plus. So this much information is enough. So this deep blue color, which is basically presence of copper 2 plus, it will react with aldehyde and it will be converted to copper plus 1. Now see, this is Q plus oxide. This is Q prick. Prick means Cu2 plus. As means plus 1, Cu2O. And aldehyde will be oxidized to RCO2H. Okay, so here intolerance you have seen Ag plus is reduced to Ag, and here what you are seeing, Cu2 plus is reduced to Cu plus. But in both reactions, one thing is common. In both cases, RCHO is converted to, that is oxidized to carboxylic acid. That thing is common. Fine. Based on this test, let's see this problem. And sorry, this is also tall. An unsaturated hydrocarbon X, unsaturated hydrocarbon, CC bond, double bond present. It is absorbing 2 hydrogen molecules. Now 2 hydrogen molecules means what? Total 4 hydrogen atom. So it also means there is presence of 2 CC double bond or 2 double bonds, not necessarily CC. On catalytic hydrogenation, it is absorbing 2 H2 molecules. Basically, it is absorbing 4 hydrogen atoms, and it also gives following types of reaction. So first information, it is accepting 4 hydrogen. So there is 2 double bonds. Second information, when it is undergoing ozonolysis reaction, you are getting A. A in presence of Tollens reagent, AgNH3 whole 2 plus. This is nothing but Tollens. Directly Tollens term is not mentioned, but if you look at the reagent, you will understand it is Tollens reagent. So after Tollens treatment with Tollens reagent, you are getting B. Now B, its name is given, hexane dicarboxylic acid. Now dicarboxylic acid, hexane. So I'm writing this 6 carbon, CO2H, CO2H. And if this is 1, 2, 3, 4, 5, 6, that means 3 position there is C double bond O. So this is the structure of B. Now, when you are treating A with Tollens reagent, you are getting B. That means in A, the structure of A, it is nothing but like this. I am writing in the same structure. Just change the CO2H to CHO. So this should be the structure of A, right? But this how you have obtained after ozonolysis. That means if there is 2 C double bond O, if I am writing this, it will help you to understand. This is 2 CHO group, and we know when we do that is if you do retro reaction for ozonolysis, these 2 CC bond that will be connected, right? Because when there is CC double bond, if you break this, you get 2 carbon. So this must be the structure. So the structure is like this. And C double bond O, that means here another CH2 will be there, because when you are doing ozonolysis, this CC bond cleavage may also take place. And even if you consider the previous structure that I have written, this is not present in any of these options, this type of structure, right? You can find some similarity with 3, but here it is CO and CC, they are adjacent, but here it is not adjacent, right? So that is why this is not possible. It must be unsaturated hydrocarbon, that is also mentioned. X is hydrocarbon, that means only carbon and hydrogen present. So this information will help you to cancel 3, right? So now you are left with 1 and 2, because structure 4 is not possible. When if it is structure A is X, you are doing ozonolysis, what you will get? You will get this type of structure. Now this, there is no CHO group. How it can react with toluene? So this is also not possible. Now you are left with 1 and 2, but we have already seen that if it is 3-oxohexane dialdehyde, it is not 2-oxo. If it is 2-oxo, then this position there should be CC double bond, but it is 3-oxo. So that is why option 2 will be correct. So full reaction now you can see. This is X, this one. After ozonolysis, you are getting 2 aldehyde, total carbon 6. And after Tollens reagent treatment, this 2 CHO group converted to CO2H. So this is 3-oxohexane dicarboxylic acid. The reagent which does not react with both acetone and benzaldehyde. So here different reagents are given: phenylhydrazine, Fehling solution, Grignard reagent, sodium hydrogen sulfate. So this is NaHSO3. Fehling solution, we know it gives positive test for aldehyde, and this is Grignard, which can react with whether it is ketone or aldehyde, that doesn't matter. But acetone is ketone and benzaldehyde is aldehyde. So NaHSO3, though it is true that NaHSO3 always prefers aldehyde and it will not react so much with acetone, but here it is mentioned it will not react at all. Though it is true NaHSO3 here the nucleophile size is very large, it always prefers aldehyde. But for acetone, as it is not very statically hindered, there will be some amount of reaction. We cannot say there will be no reaction, not at all. That is not true. So this cannot be the correct option. Then phenylhydrazine. Phenylhydrazine can react with any carbonyl. Grignard reagent can also react with any carbonyl. Only failing solution, as we have discussed in the last slide, it will react with, it can react only with aldehyde. But in this case, we have to choose does not react with both. So failing solution is correct because though it is aldehyde, but it is aromatic aldehyde. Remember, we have mentioned when it is aromatic aldehyde, there is no alpha hydrogen, so it cannot react. So that is one specialty for failing solution that you have not seen in case of tol. It is only true for failings. So it will not react with ketone because ketone is not at all aldehyde. That is the reason. But why PCHO is not reacting? Though it is aldehyde, but still it will not react because it is aromatic. There is no alpha hydrogen. Now the third reaction for aldehyde, Benedict's solution test. Now this solution, what are the actual reagent? It is mixture of copper sulfate, sodium citrate, citric acid, corresponding sodium salt, and basic medium. Now here also there is presence of CO2 plus, which is actual oxidizing agent. So see in the reaction what we have written, that is the whole mixture, what is the actual compound, details you don't have to know. Just remember it is CO2 plus which is the actual oxidizing agent. This will oxidize aldehyde, itself will be converted to red precipitate CO2O. You can find some similarity with failing test that we have just discussed, because there also CO2 plus is reduced by aldehyde and there is formation of red precipitate. Now this reaction has some interesting facts which you have not seen in the other two reactions. Though in failings there is also red PPT, final solution red, you can understand the reaction is positive. But this reaction, Benedict's, it is special because it is very sensitive. So here not just you will be able to understand whether aldehyde group is present or not, but from the color you can also understand what is the amount, that is more or less you can get some idea about the amount of aldehyde. So you can say it is obviously qualitative as well as somehow you can also call it quantitative. Okay, so as the concentration of aldehyde, that is the starting material, increases, the nearer the final color is to brick red and the greater the precipitate. Now look at these colors. When it is blue solution, it is basically negative test. That means no aldehyde is present, because original Benedict solution reagent is just like this. It is transparent, it is blue. But if there is some amount of traces of, it is written here, reducing sugar. Don't be confused. Reducing sugar means it is actually trying to say reducing group, which is nothing but aldehyde. In sugar also there is aldehyde. That is why it is written. And mostly Benedict test is done for sugar molecules. So that is why it is written in this way. So if there is trace amount of CH, then you will get this type of color, and it will change to orange red if it is moderate amount, and if there is large amount of CHO present, then only you can get this big red PPT. Now here amounts are also mentioned. How you can interpret the result of this test? If the color, that is what you have done, you have taken the sample, you are adding the Benedict's reagent, and there is color formation after heating. Now depending on this color, if it is changing after boiling to green, this is the amount, that is with respect to total amount, this is the percentage of aldehyde present. If it is changing to yellow, so see here one more, total 5 observations are there, though in the picture there is only 3, right? But in between green and orange it may be some yellow, in between orange and red, brick red, there may be red. Okay, so see number 1, if it is green 0.1 to 0.5, if it is yellow 0.5 to 1, slightly high, gradually it is increasing. Number 3 observation, if it is orange 1 to 1.5, next observation if it is red 1.5 to 2, if it is brick red, now it is the maximum amount of aldehyde, or that is it must be more than 2%. So this reaction is interesting because you can also get some idea about the amount of the aldehyde or sugar that is present. The fourth reaction, though we are discussing different distinguishing reaction, but mainly you will see these two reaction, Tollens and the Fehling. These two are mainly used. Fourth test is Schiff reagent test. Here what we take, dilute solution of aldehyde added to Schiff reagent. So this is the structure of Schiff reagent, where SO2H group is present, and this SO2H group, it reacts with aldehyde, two aldehyde molecules, 1:2. This type of adduct formation is there. So these are the two reaction sites basically, but there is also change in these positions. Detailed structure you don't have to know, just remember what color formation is there. It is magenta color formation. So if this color formation is there, it means test is positive. See, this is the color very intense, which is for formaldehyde. Now this is obviously aldehyde. Then for acetaldehyde, here also magenta color, but it is slightly less intense. And if it is acetone, this is very pale, because this is actually the test for aldehyde, not for ketone. But for acetone also you can get it, but it will take long time and very faint color generation is there. Any compound with an CHO group, it will show positive test, although sometimes aliphatic ketones, for example acetone, it might show some positive test, but the overall process for this colorization is very slow. So you can easily understand when it will take so much time for the color generation, that means it is not aldehyde. Okay, it takes long time for the pink color to emerge or magenta color, so that is why you can understand that this is not aldehyde. So this is the fourth test for aldehyde, that is distinguishing test that we have seen here. Now, why does glucose does not undergo Schiff test? Now this will take some time, so better we'll discuss it in the next class. So today we have seen oxidation reactions mainly for aldehyde and ketones, and also 4 important tests for aldehydes. The first 2 are mainly important, Tollens and Fehling's, and some related problems. Next day we'll start the next type of reaction, which is reduction reaction. We are ending the session here. Thank you for this.